This film has been prepared to explain some basics about DC machines and specifically separately excited DC generators. Those are the lecture topics given in ELE 361 Electrical Machinery course at the university. First of all, it's useful to give a definition about mechanical prime mover. Okay, this is the system of or apparatus to rotate some kind of turbine or shaft system, which also runs the electrical machine acting as a generator. It's the system that applies torque and rotates the armature of our generator. So this is one of the technical complete definitions. There are a couple of prime mover examples which can be found very frequently in our environment. One of them is water turbine. Water goes from a higher level and the weight or the mass of the water rotates the turbine, and this applies torque and generator runs and electricity is produced. This prime mover in the first case is water or waterfall. In the second case, prime mover may be an engine. It can be petroleum, gas or diesel or similar fuel engine. It also has combustion, and there's a rotation and torque applied to the electrical generator. Finally, we also can human power as prime mover. So a person or some other living creature may apply torque to rotate a system. So this is called prime mover. In elementary DC machines, which is also given in the slide number 152, we do have, okay, this is the cross section of the machine. We do have a circular rotor, which is also called armature, and two poles. This DC machine has north pole and south pole, and the flux is created by another coil which is not shown here, and the flux is traveling from one north pole to the south pole, desired to be homogeneously distributed, and under the pole it's assumed to be uniform, and outside the pole the flux is assumed to be non-existing. Flux is zero. But of course this is very theoretical and perfectionist approach. We do have leakages and other fringing effects which distort this perfection. So the axes are defined such that the theta is the azimuth between the so-called orthogonal axis with respect to the flux, etc. And it's assumed that since flux should be uniform, air gap should also be uniform, but this drawing is not perfect, so it seems as if the gap distance is larger compared to that side, which is not the case in real machines. It's always uniform, and this gap is very narrow, usually fraction or a maximum a few millimeters, and all the electromechanical energy conversion occurs in the air gap. And outside, no stator flux is present outside the poles. With these idealistic assumptions, from space angle 0 to 2 pi, okay, flux is assumed to be 0, so B field is assumed to be 0, and flux is assumed to be constant under the pole. B is assumed to be constant with a magnitude B sub m, and flux again is 0 till let's say pi minus theta 1 to pi plus theta 1 decrease. So this B field is perfectly pulsed shape or rectangular shape in idealistic conditions. So from 0 to angle 2 pi we have magnetic flux density distribution with very idealistic case. But in practice there are smooth variations between the transitions. So B field increases smoothly, decreases, and goes to the negative peak very smoothly, etc. It's also given in the slide number 152. So when the machine is rotating, it experiences first positive magnetic flux density, then negative flux density. So the induced voltage, which is the time variation or time derivative of the flux linkage, is positive here, negative there. But usually DC machines, or always DC machines, have commutators here so that the wires are commutated such that when the flux is negative, the polarity of the wire is reversed, etc. So we obtain rectified output at the DC terminals of the machine. When the armature current is commutated, the induced voltage output at the device terminals are here. Okay, here is the commutator conductors, and we do have brushes, and these brushes do have terminal outputs. Okay, at the brushes here the voltage is rectified, so as if we are rectifying the B field. Actually we are not. The B field is not like this. This is the effect of rectified output at the device terminals. So we call it DC. So one important reality is in electrical machinery, okay, in electronics this is the DC voltage. In electrical machinery this is also assumed to be DC voltage, not perfectly DC like this. And there's a definition of flux, average flux per pole, which is the flux under this area. So it's the peak flux density times two times LR. Actually this length and L, so there should be some correction here. Okay, let's say R of segment. Okay, here. So this is the rectangle. Although it's a little bit curved, we assume it's like a rectangle. So this portion and this portion creates an area here, and this is multiplied with the flux density. So this is the average flux under the pole. From the flux, we can calculate the flux linkage. It's number of turns times the flux under the pole. This number of turns is the number of turns of coil in the armature, in the rotor side. And this flux linkage, of course, it links the coil according to the azimuthal angle. like a simple machine is that, okay, and the coil is like this, and turns, and it links with the cosine of theta, whatever theta is. When theta is 90, it does not link at all. When theta is 0, it's maximally linked to the stator flux. So we have a time definition or time dependence of the flux linkage with respect to angle alpha. And this alpha, so this should be replaced by alpha here. Alpha depends on radial angular speed and time. So in any electrical machine under excitation, current carrying wires rotate under stator magnetic fields. Thus voltage is induced in the armature winding. Of course, at the same time, as well as stator windings as a counter effect. But we are mostly related with or interested with armature induction. We usually neglect the effect at the stator induction because armature wires do have much less number of windings, so their effects are minimal compared to stator to armature effects. So our formula is induced voltage is flux linkage with respect to time, or number of turns in the armature and time variation of the flux or flux linkage. If that flux linkage can be expressed as a time equation with this form, its derivative will include some constant terms. Also, one of the constant terms is the angular speed, and again it's a trigonometric function, okay, sinusoid. Thus induced voltage is proportional with the product of field flux, amplitude, and speed. So field flux amplitude is phi f, speed is omega. So this is one of the important tracks of theoretical knowledge. In practice, we cannot express everything with theories. Due to nonlinear structure of the magnetization curve, there is no analytic solution for different material curves. They have to be done experimentally. So usually experimental and graphical results play an important role to characterize a machine. What we do at that time, we obtain so-called magnetization curve. Magnetization curve is a curve horizontal such that it's the B field in with respect to H field is plotted, or equivalently H is created by current, field current. So horizontal axis is current and vertical axis is induced voltage, which is also related with the B field. So usually magnetization curve is a curve such that it's drawn with for field current with respect to induced voltage. That induced voltage is sometimes shown with E sub I. Usually it's shown with E sub A, stands for armature induced voltage. It has usually starts with non-zero point, and some part is almost linear. Then there's a banding region and reaches a saturation. This region is saturation region, and this region is avoided for proper operation. This curve is obtained under constant speed, so during the experimental obtaining of magnetization, omega is kept constant, and IF, field current, is our independent variable, plotted in horizontal direction, and this region is almost linear, so induced voltage is almost proportional to the number of turns times field flux and rotation. So rotation is kept constant. Okay, and that flux is directly proportional with IF. So there's a direct proportional relationship between these two variables at this region. This point is not origin. When we rotate the machine under no excitation, we still obtain some induced voltage. Okay, this is due to residual magnetization. So inside the DC machine, the magnetic material has some residual magnetization, and they behave like magnets, although there is no electromagnetic current inside the machine. So that produces induced voltage with a low value, 5 or 10 or 20 volts or so. So with this magnetization curve in hand, we can characterize the machine mostly. We also need torque relationships as well. So from this curve, by using magnetization curve, when we operate in the linear operation, we may assume that if the machine is run at this speed, at these conditions, etc., we may assume some losses do not occur, they are neglected. So mechanical power equals to the electrical power input from this machine. So whatever that we give electrically, we obtain its mechanical power output, of course, plus losses. And these losses are neglected for simplicity at this moment. Electrical power input is the armature voltage times armature current. Mechanical power output is mechanical torque and rotational speed. From the previous slide, the induced voltage can be expressed as some constant times flux times speed, which was shown in the previous one. So, assuming IF is constant, assuming omega is constant, because this operation curve is obtained at constant speed, Ka times omega can be replaced by another constant factor, Kf. So induced voltage is directly proportional with the field current. When we replace this into the equation above, we do have two K constants in omega times field and armature currents, and rotational speed cancels out in both sides. So we do have a torque expression constant times the multiplication of two currents, stator current and armature current. So this is a important outcome. So we have separately excited DC equation. Let's remember what a separately excited machine is. Separately excited machine is this. We do have some kind of variable field voltage source, and through the field windings, field current passes, and armature is drawn like this, and there is a series resistance of the armature windings and induced voltage, and this is the electrical terminals of the generator, and there's a prime mover which rotates the machine with speed, And at the terminals we do have load and the electricity is supplied from this machine, and this generator is so the boundary of the so this is our generator. So let's emphasize it. So this is our generator. Prime mover is outside the generator. Separately excited field voltage source is connected through field terminals, and armature terminals are connected to the load so that load is fed and electrical power is obtained at the output. Electrical power is obtained. So mechanical power is fed into the system, electrical power is the output. So mechanical power input to the system. Input, and this is P out. Okay, so this is the separately excited DC generator. The induced armature voltage equals to the RA plus RF times IF plus RA IL. So it's better to express VL IL characteristics